Hi, I'm Norman Wildberger. Today we are going to continue now in this series on Universal Hyperbolic Geometry. We're in the second part of this series where we're branching out to adjacent connected areas to the subject. In particular, we're interested in spherical and elliptic geometries and trigonometries. I have already summarized for you the basics of classical spherical trigonometry. And I've told you that we're going to aim towards a new and simplified way of doing that. And today we're going to show you what that new and simplified way looks like. Okay, so it's very exciting. So we're going to be looking at elliptic trigonometry, and spherical trigonometry is a sort of a consequence of that, closely related but a little bit different. So the fundamental object is an elliptic triangle, and we're really talking about the context of projective geometry here because we're interested in lines through the origin in three-dimensional space. So here is a crude model of an elliptic triangle. You should think of this as being the origin, and here we have three different lines through the origin, forming an elliptic triangle. So this might be the line A, the line B, the line C, and this configuration itself is the triangle. Now, when we want to visualize it, one way of doing that would be to create a sphere centered at the origin and have a look to see where these three lines meet that sphere. They would do so in three pairs of opposite points, or antipodal points. And on the surface of the sphere, we could join those points with great circle arcs to form what is usually more called a spherical triangle. So for example, if the sphere was roughly about this big, and these three were points on the sphere, then we could connect these 3 points here, say, to form a triangle on the surface of the sphere. But we should keep in mind that we're really thinking about these things as lines primarily and not points on the sphere. Those are secondary aspects of what we're talking about. All right, so this is going to be useful to anybody really who works in three-dimensional geometry, where directions and basic configurations having to do with spherical trigonometry are important. So physicists, NASA engineers, video game creators, geometers, chemists, computer scientists, anybody with an interest in three-dimensional geometry is going to find the formulas that we're going to lay out today interesting and very useful. All right, so the main object is such an elliptic triangle or a spherical triangle, and the outcome is going to be new simplified laws for spherical trigonometry. And the remarkable thing that's going to happen, that's going to unfold before us, is that these new laws for spherical trigonometry, or for elliptic trigonometry, end up being exactly the same laws that we've already seen in universal hyperbolic geometry. So they will be nothing new to those who have been already watching this series. But in fact, this lecture here today will be somewhat independent from the rest of the series. You will not have to have watched any of the other videos to be able to follow the discussion here. But hopefully it will motivate you to go back and check out that universal hyperbolic geometry material in the earlier lectures. So let me remind you just some basic facts about elliptic geometry. We're working in three-dimensional space, which you can think of as a three-dimensional vector space. The main objects of interest are lines and planes through the origin. We have our x, y, and z axes as usual. A point in the space will usually be denoted by the capital letters and a triple of numbers enclosed in square brackets. Whereas a vector, like this vector v, will be enclosed in round brackets, and there may be a little vector sign above it. And the line that's determined by the point A and the origin, that line there, or in other words the line that's determined by the vector v, will be denoted in this way. It really only depends on these three numbers up to a multiple, so it's really the proportion x to y to z that specifies that line. And so we encode the information by calling the line A to be the proportion x to y to z enclosed in square brackets. And we'll often call that a projective point, or just a point in this projective story. And one slight condition that we need to have satisfied is that the three numbers x, y, and z are not allowed to all be 0. One of them or two of them can be, but they're not all allowed to be 0, because then we would not have any real direction. All right, so if we just have one projective point, say A1, x1 to y1 to z1, just that single line in three-dimensional space, then there's nothing to measure. Things get more interesting with 2 points. So we have 2 points, say A1 and A2, with coordinates x1 to y1 to z1 and x2 to y2 to z2 are given. Then there's exactly one thing to measure, which is the spread between these two lines. So we're talking now about a situation like this, where we have two lines passing through the origin. Now, if you're a classically trained student, you might say, well, the thing we want here is an angle. But for sure, an angle is not the right notion. You have to get used to that idea. Very important idea. If we were measuring angles, we'd have to decide whether it's this angle or this angle or this angle or this angle that we're interested in, or maybe this one, or maybe this one, etc. Angles are notoriously difficult to actually compute with. We're going to be measuring things much more algebraically and pleasantly with this concept of spread that comes from rational trigonometry. So the spread between these two lines is going to be a number that we're going to associate to these 2 points. And because we're calling these things points now, we're going to refer to this number as a quadrance. So this is a projective kind of variant to the affine rational trigonometry that we talked about in some earlier videos. Here the points are actually these projective points. And the quadrance between two projective points is in fact really the classical affine spread between the two lines that really represent those projective points. And to make it clear that this notion of quadrants is different from the affine notion of quadrants, we're going to use a small q instead of a capital Q. In the same way that we're using small letters A1 and A2 for the projective points, instead of capital A1 and capital A2 for honest-to-goodness standard affine points. So there's these two sides of the coin, the affine story and the projective story. We are now discussing the projective story, where the notation is in some sense sort of opposite to what it is in the affine story. It's a bookkeeping device that allows us to minimize confusion, hopefully. So how are we going to get at this projective quadrants between these two projective points? So here's A1 and here's A2 in this three-dimensional space. And this projective point is determined by a vector in the affine space, say V1. And this projective point is determined by another vector, V2. And of course, those vectors are not unique. They're determined up to a multiple. All right, let's call those vectors V1, coordinates x1, y1, z1, and V2, x2, y2, z2. I now want to define the spread between these two projective points in terms of these numbers. And the main thing that we're using, which will not be a surprise to you, is the dot product between the two vectors. Sometimes called the dot product, other times called the inner product, or sometimes the scalar product. Okay, it's a number created from the two vectors. And it's the product of the x coefficients plus the product of the y coefficients plus the product of the z coefficients. And it has a linear algebra aspect too. So if we think of this as a matrix, a 1×3 matrix, and this one also, then another way of thinking about that is the product of this matrix times the transpose of that matrix. So that vector times the transpose of the vector is exactly the same number. That's sort of how you multiply matrices. And I'll just remind you of a few basic properties of this dot product. First of all, it's symmetric. It doesn't change if you interchange the order of v1 and v2. And secondly, it's linear, both in the second variable and in the first variable. And what that means is that v1 dot v2 plus v3 is the dot product of v1 with v2 plus the dot product of v1 and v3. And there's a similar rule for the linearity in the first variable. Alright, so how are we going to use this dot product to define the projective quadrants between these two projective points? Well, it will not be a surprise to those who have been watching the series up till now. We're going to use essentially the same kind of formula that we've already used before. So we're going to define the quadrants between these two projective points, A1 and A2, as 1 minus, now this ratio of v1 dot v2 all squared divided by the quadrants of v1 times the quadrants of v2. Where these are capital Q quadrances, that is affine quadrances, and that's just defined by this simple equation that the quadrants of a vector is v dot v. So I could also have put down here v1 dot v1 times v2 dot v2. And the beautiful thing about this expression is that it really is independent of scaling of the vectors v1 and v2. So if I multiply v1 by, say, 5, then this numerator gets multiplied by 5 squared, or 25. But because of this v1 dot v1 term in the bottom, the denominator also gets multiplied by 25, and so the whole expression is unchanged if we scale either v1 or v2, or both of them. So this is really a projective quantity. It looks like it depends on the vectors v1 and v2, but it doesn't. It only depends on the lines that we've chosen. It's called the projective quadrants between A1 and A2, and we'll generally drop the projective because we're working in this projective setting. We'll just call it the quadrants between A1 and A2. Now, for those students who have taken linear algebra before, maybe I'll just say a few words that this is not too unfamiliar, I hope. If we didn't have the 1 minus here, and we just looked at this expression here, you would recognize that this is the square of the cosine of the angle. Okay? So if we took a square root here, then we'd get a v1 dot v2, and then there would be a square root of the quadrants, which is the length of v1, times the square root of the quadrants of v2, which is the length of v2. And so that would then be the cosine of the angle, supposedly. And then to find the angle, you would have to take a cos inverse, get your calculator and press some buttons, get some decimal approximation out. And that's the quantity that you usually would work with if you were a traditional student in a traditional university in the year 2013. Of course, 100 years from now, they'll be doing things completely differently. Nobody will be doing that. They'll all be using this, of course, because this is so much simpler, more computationally friendly, and just conceptually, orders of magnitude better. The quadrants between two lines, a fundamental formula. It measures how far apart the two lines are. If they're in the same direction, if v1, say, equals v2, well, then this quantity and this quantity are the same. And we're going to get 1. So we get 1 minus 1, which is 0. So if we have two lines which are pointing in the same direction, we're going to get 0. On the other hand, if we have two lines which are perpendicular, then the v1 dot v2 term is 0. And so then we're going to get 1. So this is a number that ranges from 0, if the two lines are the same, all the way up to 1 if the two lines are perpendicular. And if you keep going, then it goes back down to 0. Okay. It just acts like a usual spread in rational trigonometry in the plane. It's algebraic, it's beautiful, it's the right concept, for sure. So let's look at an example. If v1 happens to be the vector 1, 2, 3, and v2 is the vector 4, minus 1, 2, then the quadrants between the two lines determined by those two vectors, we sometimes will use this notation that v1 with a square bracket around it is the line in the direction of v1 from the origin. And similarly, there's the line in the direction v2 from the origin. So then what's the formula? We have to take 1 minus the dot product of these two vectors. So that's 1 times 4 plus 2 times minus 1 plus 3 times 2. All of that squared. So that's 4 minus 2 plus 6. That would be 8 squared, which is 64. Divided by the quadrants of this vector, which is 1 squared plus 2 squared plus 3 squared, times the quadrants of this vector, which is 4 squared plus minus 1 squared plus 2 squared. And we work that out, and we get 115 over 147. We get, as we want, a correct answer, which doesn't involve any irrationalities, and which we can write down completely without any fussing, without any waffling about infinite this or infinite that. There's an important alternate form for the spread, which is going to be very useful for us, which also shows that this is intimately tied up with fundamental linear algebra. So let's have a look at these two vectors that determine two lines. And let's create a matrix object out of those two vectors just by writing those two vectors as rows of a 2 by 3 matrix. Let's call that matrix A. And for short, I might write it like this. So the first row is the v1 vector, and the second row is the v2 vector. Okay, so that's just a short way of writing that if I don't feel like writing down all the coefficients. All right, so an interesting thing to do when we have a matrix like this is to look at A times A transpose. So here's A, and here's A transpose, what you just get by flipping things on the diagonal. So V1 was going horizontally here, so here's its transpose, which is now going vertically. And here's V2 going horizontally, and here's V2 transpose. And when we multiply A times A transpose, which is a very, very common and important operation in linear algebra, what we're going to get is a matrix of inner products. Because this first row times this first column is just the dot product between V1 and itself. So it's V1 dot V1. The first row times the second column is the dot product of V1 with V2. The second row here and the first column gives us V2 dot V1. And I've rewritten that as V1 dot V2 because it's really the same as this, and that makes the symmetry obvious. And finally, the last entry is V2 dot V2. Sometimes called a Gram matrix. It's a matrix of inner products that you get from the two vectors here by forming A times A transpose. And we're going to call this 2 by 2 matrix capital V. All right, so now we can have, just make this observation, that the quadrants between A1 and A2 is just the determinant of V divided by the quadrants of V1 times the quadrants of V2. Why is that? Well, what is the determinant of V? It's this times this minus this times this. Well, this is just the quadrants of V1, and this is just the quadrants of V2. So this term times this term is really just the same as that denominator. So it's this times this minus this thing squared, and that's just 1 minus V1 dot V2 squared over Q of V1, Q of V2. So it's an immediate consequence. But it, again, sheds light on the sort of fundamental aspect of this spread. Okay, it's just a determinant of the Gram matrix renormalized. So if you've done some linear algebra, you start to appreciate that this kind of thing is almost sort of the simplest thing that you could possibly do, really. Okay, there's nothing that really that works that is really simpler than this. If you want to associate a number to a pair of projective points, or vectors up to multiples. Let's introduce a bit of shorthand notation, which I found very useful in this subject, which is to agree that the dot product between the vector vi and the vector vj will be denoted v sub ij. Now if you think about that matrix V that we talked about on the last slide, then this is exactly in keeping with that matrix, because the ijth entry of that matrix is exactly vi dot vj. Okay, so now it's time to move up to the real object of interest, which is not a pair of projective points, but rather a triple of projective points. The elliptic triangle that we're trying to study. So here is our three-dimensional space, and now we have three lines, line A1, line A2, and line A3, each of them determined by three direction vectors, V1, V2, and V3. And of course, they don't have to be in this direction, they can be in that direction too. We can multiply these vectors by any non-zero scalar to get an equivalent, equally valid direction vector. Alright, so we encode that this way. We say that the projective point A1 is the line or projective point determined by V1, A2 is determined by V2, and A3 is determined by V3. And we encode all the information in this 3 by 3 matrix called A, whose rows are the three vectors V1, V2, V3. And I won't always write the vector sign over there. Here is the transpose matrix, A transpose, which has the transpose of the vectors now down the columns. And just as we did before, we're going to multiply A times A transpose. And when we do that, we're going to get a gram matrix of inner products, of dot product between the three vectors V1, V2, V3 and themselves. So this entry here will be V1 times V1 transpose, which is V1 dot V1. And we've agreed that we're going to call V1 dot V1 just V sub 1, 1, which is a number. It's a dot product between the vector V1 and itself. While this V1, 2 is the result of multiplying the first row here by the second column here. So it's the dot product of V1 with V2, which we're agreeing is V sub 1, 2, etc. So we have all these dot products, and this is a symmetric matrix because the dot product is symmetric. And because whenever you take a matrix A and you multiply it by its transpose, that is a symmetric matrix, always. And we're calling that symmetric matrix V, just as we did before. All right, what are we interested in with this elliptic triangle? Well, first of all, we're interested in the three separations between the three projective points. The projective quadrances formed by the three pairs of projective points. So we're going to call them Q1, Q2, and Q3. And Q1 is the quadrants between A2 and A3. And what is it? Well, it's really just determined by this part of the this big matrix. It's V22, V33 minus V23 squared over V22, V33. We're just applying the formula that we just derived to the two lines A2 and A3. And here are the various inner products made by those two vectors, V2 and V3. Here's the determinant on the top, and here's the product of the quadrances on the bottom. And exactly in a similar way, just changing the indices, here's Q2, which is the quadrants between A1 and A3. And here's Q3, which is the quadrants between A1 and A2. And they're also given by essentially a determinant, a 2 by 2 sub-determinant or minor of this matrix. So here is V11 times V33 minus V13 squared. And over here we get a V11 times V22 minus V12 squared, all over the corresponding product of quadrances. So those are the three projective quadrances formed by these three projective points. All right, so that's half of the story. The other half has to do with the spreads of this elliptic triangle. So far we've talked about the three quadrances. Now we want to talk about the three spreads. And what's involved there is understanding the relationship between the triangle and its polar triangle. And it turns out that that's intimately connected with the inverse of the matrices that we've been talking about. So first let's make its definition that two elliptic triangles, say A1, A2, A3, and B1, B2, B3, are polars precisely when B1 is perpendicular to both A2 and A3, B2 is perpendicular to both A1 and A3, and B3 is perpendicular to both A1 and A2. And equivalently, we could restate that by saying, well, it's the same as saying that A1 is perpendicular to B2 and B3, because here's A1 perpendicular to B2, and here it's perpendicular to B3. And A2 is perpendicular to B1, B3, and A3 is perpendicular to B1 and B2. So there's a perfectly symmetrical relationship between these two elliptic triangles. And geometrically, what does it mean? Well, okay, here's an elliptic triangle again. Okay, and let's roughly try to illustrate what the polar triangle would look like. Okay, so we're looking for another triangle. Say the whose first direction is perpendicular to the second and third of the lines here. So say this is the first line, the second line, and the third line. Then B1 has to be perpendicular to A2 and A3. So it's going to be a vector in that direction. Okay, it's perpendicular to the plane formed by these two. So this is really the normal vector to the plane spanned by those two vectors. All right, so B2 is going to be a normal line to A1 and A3. So it's going to be in this direction here, perpendicular to this plane. Okay, I'll stick it there. And finally, B3 is supposed to be perpendicular to A1 and A2. Well, here is A1 and here is A2, so perpendicular to that will be there, roughly like that. Okay? So the original triangle, A1, A2, A3, and here's the polar triangle, B1, B2, B3. And it's a symmetrical relationship between these two elliptic triangles, these triples of lines through the origin, really geometrically. So algebraically, we can understand this very nicely with these matrices that encode the elliptic triangles. So let's say A is the matrix whose rows are V1, V2, V3, where V1, V2, and V3 are vectors in the directions A1, A2, and A3. And here is the corresponding matrix B, whose rows are W1, W2, and W3, which are vectors in the directions of B1, B2, and B3. Then we have this following result that connects this idea of polarity to the notion of matrix inverse. Okay, it says that if the inverse of this matrix is the transpose of B, so if A inverse equals B transpose, then the two elliptic triangles are polars. All right, and the proof. Well, if A inverse equals B transpose, then it means that if you take the matrix A and you multiply it by B transpose, and here's B transpose, what you get when you write the vectors W1, W2, W3 down the columns. So if A inverse equals B transpose, then this is A and this is then the inverse of A. So when we multiply them, we're going to get the identity matrix. And what does that tell us about the dot products between the vectors v and w? Well, it tells us that v1 dot w1 is 1, while v1 dot w2 is 0 and v1 dot w3 is 0. In other words, v1 is perpendicular to w2 and w3. And similarly, v2 is perpendicular to w1 and to w3, and v3 is perpendicular to w1 and w2, as you see by those zeros there. So this matrix product of getting the identity exactly encodes the information that these three vectors and these three vectors, or the transpose of those vectors, are polar elliptic triangles. That's another way of thinking about what matrix inverse is representing geometrically. It can be a very useful way of thinking about the inverse of a matrix. All right, so let's have a look at the trigonometry now associated to one of these elliptic triangles, A1, A2, A3. So we know that the polar triangle B1, B2, B3 of, say, this triangle has points perpendicular to the sides of A1, A2, A3. Here's just a picture again of A1, A2, and A3. Now, for more, to remind yourself about this polarity business, you can have a look at UHG 37. All right, so here's our elliptic triangle, A1, A2, A3, and it has quadrances. These are the quadrances between pairs of these lines. Okay, but now we also have this polar triangle, which is introducing another three quadrances. So the quadrances of the polar triangle, we're going to define them to be the spreads of the original triangle. So let's have a look at this example. So here we have an elliptic triangle, say A1, A2, and A3. And say then B2 would be the line perpendicular to A1, A3. So here's A1 and here's A3. That means that B2 would be, say, in this direction. There's B2. While B3 would be the perpendicular to A1, A2. Here's A1, here's A2. So there would be B3. Okay. And what we're saying is that the quadrants between these two, okay, the quadrants between those two is really a reflection of the separation between the plane A1 and A3 and A1 and A2. Okay. So on the diagram, that would be the plane between A1 and A2 is represented by this great circle on the sphere, and the plane formed by A1 and A3 is represented by this great circle. And the spread between those planes, we would want to think of that as the separation between those two lines on the great circle. That number is just represented by the quadrants between the corresponding polar points. So this is very analogous to what we did in the classical spherical trigonometry, where we defined the angle between two lines of a spherical triangle in terms of the angle formed by the normals. So we're doing exactly the same thing here. We're saying that the spread between these two projective lines can be thought of as being the quadrants between the normal lines. So the quadrants between B2, B3, we're calling that capital S1 because it's a projective spread. Quadrants between B1, B3 is capital S2. The quadrants between B1 and B2 is capital S3. We call these the spreads of the triangle A1, A2, A3. And here are then the 6 main quantities that we're interested in elliptic trigonometry. We have a triangle A1, A2, A3. We have 3 quadrances, Q1 opposite A1, Q2 opposite A2, Q3 opposite A3. We have 3 spreads, S1 at A1, S2 at A2, S3 at A3. And the million-dollar question is, what are the relations between Q1, Q2, Q3, and S1, S2, and S3. And somewhat surprisingly, it seems that no one has really thought about these relations until, until relatively recently. It was only with the advent of rational trigonometry that we were able to look at this and recognize that this is really the key question in this trigonometry. All right, an exercise to get you practicing computing some quadrances, computing some spreads, and finding polar triangles. So here are three projective points, A1, A2, A3, 1, minus 1, 2, 3, 1, 1, 1, 2, minus 2. And first thing you want to find is the quadrances formed by those 3 points, the quadrances of the elliptic triangle A1, A2, A3. And the second thing is to show that the polar triangle is given by B1, B2, B3, where B1, B2, and B3 are these things here. So I've calculated for you. Just check that that's true. So these ones here, 4 minus 7 minus 5, minus 2, 4, 3, 3 minus 5 minus 4. And then you can calculate the quadrances between these 3 are then, by definition, the spreads of the original triangle. So S1, which is the spread of the original triangle A1, A2, A3 at the point A1, is by definition the quadrants between B2 and B3, and that's 3 over 725. S2 is 11 over 4,500, and S3 turns out to be 241 over 290. So you can check those things. And it's easy to see that you could easily create lots of explicit examples of elliptic triangles and compute all the quadrances and compute all the spreads. So that the formulas that I'm now going to show you, which are the main formulas in the subject, are ones that you can verify directly by hand with just pen and paper. All right, so what are the main laws? Moment of truth. The laws of elliptic trigonometry. The new laws, the completely algebraic laws, the rational laws, the laws of the future. Okay. Suppose A1, A2, A3 is an elliptic triangle with quadrants Q1, Q2, Q3 and spreads S1, S2, S3. So we're talking about the situation here, A1, A2, A3, forming elliptic triangle, and here are the various 6 quantities and their representation in this sort of schematic diagram. Well, there are really 2 laws, but one has a sort of a dual aspect, which I'll write down as well. So the first law is the spread law, which says that Q1 over S1 equals Q2 over S2 equals Q3 over S3. It will not be a surprise to you that have studied a bit of rational trigonometry, either in the affine setting or in the hyperbolic setting. The main law is the cross law, one of the most important formulas in all of geometry, in fact of all of mathematics, I would have to say. And it is that S1, Q2, Q3 minus Q1 minus Q2 minus Q3 plus 2 all squared equals 4 times 1 minus Q1 times 1 minus Q2 times 1 minus Q3. And that's the formula involving S1. There's a similar formula if we replace this term with S2, Q1, Q3 and leave all the rest unchanged. Or another formula if we replace it with S3, Q1, Q2, everything else unchanged. So there are really 3 cross laws, but they're all pretty well exactly the same. And there's a dual form. The dual form is that we can just replace all the Q's with S's. There's a complete symmetry between the quadrances and the spreads here. It's a very attractive feature of this projective form of rational trigonometry. Quite different from the affine story. So it's really exactly the same formula, except now it's Q1, S2, S3 minus S1 minus S2 minus S3 plus 2, all squared, whole thing squared, equals 4, 1 minus S1, 1 minus S2, 1 minus S3. Now there are some other laws, like Pythagoras' theorem and Thales' theorem and so on, but it will turn out, we'll see, that they're really consequences of these ones. So these are sort of the master formulas that control everything. And unlike the classical laws of spherical trigonometry, like the sine law and the cosine law, which are analogs of these, here the symmetry between the first cosine law and the second cosine law is a complete one. It's a complete duality. And most remarkably, perhaps, that these are exactly the same formulas as those who have been following this series up till now will recognize immediately. You'll say, oh, here are those great formulas that we already know and love. No new technical formulas are required to make the jump from hyperbolic geometry to spherical or elliptic geometry. It's the same formulas. And not just analogous, like, well, we replace cosines with coshes and sines with shines and so on. No, it's exactly the same formulas. Very powerful. That's why it's universal geometry. All right, so an exercise for you. We'll verify these laws for the previous example where we've already worked out what all the quadrances and spreads are, so you can check to see that they hold. And you can compute some other triangles, lots of triangles, and you can verify that these laws always hold. Okay, they look pretty complicated. Surely the proofs are pretty involved. Well, we'll see next time that the proofs, in fact, are not that involved. The framework that we've established in today's lecture will make proving these formulas a piece of cake, surprisingly. So it's all very, very simple. It's order of magnitude simpler than the classical theory. And it will turn out to be much more powerful and more general. Okay, so this is the right way of thinking about a very important subject. So give it some serious thought. And next time we're going to look at how you establish these formulas, basically using just some elementary linear algebra. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.